Hey guys, welcome back to another lecture video for Chem 115. In this video, I'm going to talk about titrations and titration curves. And I'm going to go over, what they are, the theory behind the calculations, and their relevance in chemistry. In the next video, we will take a look at how to quantify and build titration curves from scratch. So let's get started. So to introduce this topic, we're going to first ask ourselves this basic question: what is titration? And so titration is a lab technique to quantitatively determine an unknown concentration of either an acid or a basic solution. And so we want to quantify the concentration, which is typically in molarity units. Of an unknown acidic solution or unknown basic solution. Okay? So that's the main point of titration. So hopefully you guys have performed titrations in first semester general chemistry. Titration is something that is commonly done in a first year general chemistry course. And so let's go ahead and review the parts. So this instrument here that I've drawn, this is known as the burette. And the burette typically holds your titrant. Okay, so we're going to add on to this definition by introducing ourselves to terminology. And so the titrant is typically the substance that the concentration is known. Or standardized. So hopefully you guys were able to standardize an acidic or basic solution in the first semester of general chemistry. And so this burette is graduated. In other words, there's increments. And so when you fill up this burette, you typically fill it up close to the very top. Oops. Okay. And as you guys transfer your titrant into this Erlenmeyer flask, it's measuring the difference. So let's just say that this is the initial volume. It's measuring the difference of the change in volume. In other words, the increments are being used to quantify how much volume you've added into the Erlenmeyer flask. And so, long story short, the volume used during a titration is known. Okay? Because you can simply read the markings on the burette and take the difference between the final and the initial. Okay. Now, inside this Erlenmeyer flask, and so since Erlenmeyer flask is just such a big word to write, I just say E-flask, just to abbreviate it. And so in this Erlenmeyer flask, that's going to contain the substance that you do not know the concentration of. So you have an unknown concentration of a specific substance. And so since this is the substance that you're analyzing, this is known as the analyte. Okay. And so I'm going to be using these two terms consistently throughout this video and the next few videos that covers titration curves. Titrant and analyte. So titrant is inside the burette and the analyte is inside the Erlenmeyer flask. And so when you guys are performing these titrations, you guys are going to add the volume of burette, or I'm sorry, the volume of the titrant drop by drop. And you guys are going to keep on adding them drop by drop until you see a change in color, right? And we'll talk about that change in color more heavily later down this lecture. But once you guys get a change in color, let's just say your indicator is phenolphthalein, and the solution will turn from colorless to pink with phenolphthalein, then that's going to mark your endpoint. Okay. And so you have a change in color. Okay. And so this is a physical cue to let you know that the reaction has completely been neutralized. Okay. All right. And so now that we've kind of reviewed the general pieces, the general terminology of titrations, let's go ahead and address this question. How is it possible to determine the concentration of an unknown substance? And so you guys can, so for us to address this, let's take a step back. Concentration in chemistry refers to the molarity of the solution. And molarity is always equal to moles of solute per 1 liter or per liter of solution. Okay? So it's always moles per liter. And so if you guys can determine both of these pieces, and then you guys divide these numbers together, then you guys will obtain the molarity of this unknown substance. Okay? And so how do we determine the volume of the solution? Well, the volume of the solution can be determined by how much of it we added to the Erlenmeyer flask. So how much of the analyte is placed inside the Erlenmeyer flask. And that's something that you will measure out on your own using a graduated cylinder. So let's just say that we have 5.00 mils. And so if we added 5 mils of the analyte in this Erlenmeyer flask, then that means that's going to be the volume of the solution. And so here in this case, we'll just have to convert 5 mils into liters. And so this is going to be 0.0. So remember, milli is times 10 to the negative 3. So we're going to have to move this decimal 3 places to the left. 1, 2, 3. So this is going to be 0.00500 liters. Okay. And so that's pretty simple. We measured how much analyte we're using. We converted that into liters. We're going to plug that into the denominator because that's going to represent the volume of the solution. And so the more difficult piece to this puzzle is determining the moles of solute that's inside that solution. So of this 5 mil, how many moles of solute are there? Okay. And so this is where titration is going to kick in. And so we didn't even do a titration in this specific discussion. We just determined the volume of the solution that we use, and we plug that into the denominator. And so to figure out the number of moles of solute, we're going to have to rely on titrations and the theory behind it. And so it turns out that when you guys perform a titration, the main reaction that's occurring is an acid-base neutralization reaction. And so what that means is that you have some type of acid. And so I'm using HA to represent whatever acidic compound we have. It can be monoprotic, diprotic, whatever. But we have an acid, and we're going to react it with a base. And whenever you have an acid reacting to a base, if you guys recall, the main components of a neutralization reaction, we're going to take this hydrogen, the acidic component, and we're going to combine it with hydroxide to form water. And everything else just kind of comes together. And so this is our salt. And so if you guys look at the product, do we see any more protons or hydroxide ions? And the answer is no, we don't. And so that tells us that the solution has been completely neutralized. And so what that means is that if we have equal moles of base to equal moles of acid, then the only product that we're going to get is water and the salt. And we know that the salt of these acids and bases, if they're strong acids, strong bases, are not going to affect the pH of the solution. And so that's really cool. The reason why is because if we know the number of moles of base or the number of moles of acid, then we can do a mole to mole ratio and perform stoichiometry to convert moles of acid to moles of base, or moles of base to moles of acid. Okay. But the main idea is that we're able to determine the moles of the substance, and we're going to use that value and plug it into the numerator. And then once you guys have the moles of the solute, whether it be an acid or a base, you just divide it by the total volume that you initially use, and that's going to give you the concentration or the molarity of this solution. And so hopefully that theory, that explanation makes sense in the theory behind titrations. Okay. And so just to kind of put this into perspective, let's just go ahead and look at an example. And so, for example, you have hydrochloric acid reacting with sodium hydroxide. Okay, and so hydrochloric acid is a strong acid, and sodium hydroxide is a strong base. And so let's go ahead and add in some more terms that we discussed earlier, such as titrant and analyte and all that stuff. And so imagine that we have hydrochloric as our analyte, okay? And I'm just choosing hydrochloric acid because that's the first thing that I see. If I wanted to make my sodium hydroxide the analyte, I can. It just really depends on the solution that you're trying to analyze. So let's just say for now that my hydrochloric acid is my analyte. Okay? And so what that means is that I don't know the concentration of my hydrochloric acid. And this is what I want to figure out. But what I do know is the total volume that I've added of the analyte, because I just measured that out and put that in my Erlenmeyer flask, right? And so I'm going to measure out some amount of my analyte, and I'm just going to put it in here, and the unit of measurement will be volume. And so let's just say that this sodium hydroxide is going to be our titrant. So that's going to be found inside the burette. And since it's found in the burette, then that implies that we do know, so I'm going to put here known concentration or molarity. And since our burette is graduated, then we can determine the change in volume, and that's going to equal to the volume used. Oops. Okay. And so if you guys take the concentration and you multiply it by the change in volume, what you guys get is the number of moles of the base. Okay? And so let's just say in this example, we used 3 moles of the base. Well, for us to completely neutralize the acid that's found inside this sample, inside this Erlenmeyer flask, we would have to have an equivalent or an equal number of moles of acid to completely neutralize the moles of base that we added. So 3.00 moles of the acid should equal to the moles of the base. Okay. And so if we know the moles of the acid, then we can go ahead and plug that into the numerator for the molarity equation. And since we know how much volume of the acid that we added into the Erlenmeyer flask, we can just go ahead and divide both of these values, and that's going to give us the concentration of our analyte. Okay. And so the key idea is that these titrations that you guys have performed in first semester general chemistry, it's nothing more than an acid-base neutralization reaction. And it's very important for us to understand that, because we can quantify the number of moles of substance that we have in our Erlenmeyer flask by adding an equal amount of moles of substance that's in our burette. Okay. All right. And so hopefully that refreshes your knowledge of titrations. And in terms of calculation, if the number of moles equals to the number of, if the number of moles of acid is equal to the number of moles of base, then what that means is that you guys are at the equivalence point. Okay. So you are at a point in your titration when the stoichiometric relationship or equivalence is 1-to-1, right? So you have equal number of moles of acid equaling to the same number of moles of base. So this is known as your equivalence point. And so your equivalence point, typically, if you guys are in lab, when you're mixing an acid and a base, it's typically colorless. And so to signal that you've reached the equivalence point, you're going to utilize a chromatic compound. And so, for example, you're going to use like phenolphthalein. So you're going to use a pH indicator to signal the equivalence point. And so sometimes we interchange these terminologies. They're synonymous to each other, but the equivalence point signals the endpoint in your titration. And so when your indicator or your solution has turned to a different color, then that means that you've reached the endpoint in the titration. And at the endpoint, you've, on a molecular basis, you've reached the equivalence point, meaning that you have equal number of moles of acid to equal number of moles of base. Okay. So hopefully you guys kind of understand how all three of these concepts kind of tie in with each other. Okay. And so at the endpoint or equivalence point, You can streamline your titration calculations by using a modified dilution equation formula. And so in the first semester of general chemistry, perhaps your professor wants you to quantify or to determine the concentration using dimensional analysis, where you're setting up mole to mole ratios, you're using molarity as a conversion factor, et cetera, et cetera. However, you guys can streamline your calculations at the endpoint or equivalence point by using a modified dilution equation. And that equation is MA times VA is equal to MB times VB. Okay? And this is where a lot of students kind of fall short. They do not incorporate the stoichiometric relationship between acid and base. And so for you to not fall into that trap, you need to make sure that you need to divide the MAVA by NA. Okay, so this is an N. Maybe I'll just capitalize it. Okay. And I'm going to divide this by NB. So what does M, V, and N mean? And so M represents molarity. V represents the volume. And so that kind of goes on the same side for, that applies to all the M's and the V's that you guys see. And N is equal to the moles of whatever that substance is. Okay. So this is typically the mole to mole ratio. So you guys are going to grab these values from the coefficient in your chemical equation. Now, what does A mean, right? So A, and I'll go ahead and use capital A just to be consistent. Make sure everything is capitalized. So A is your acid. Okay? And B is your base. And so what this is basically telling you is that if you guys are trying to solve for the molarity of the acid, then you just need to determine the volume of the acid, the stoichiometric equivalence of the acid from the balanced chemical equation, determine the molarity of the base, the volume of the base, and the mole to mole or the coefficient of the base from your balanced chemical equation. And then all you have to do is just solve for MA using algebra, and then you're done. Now, I'm going to go ahead and just leave this equation as is. I'm not going to go through an example in this video lecture. We're going to be using this equation when we build our titration curve. So there's going to be a lot more practice using this equation later down the line. All right. And so hopefully this topic helps introduce just what titrations are, or helps revisit it if you haven't done titrations for quite some time. I definitely encourage you guys to check out some YouTube videos, and you guys will actually be doing this in lab next week. And so feel free to check out some YouTube videos just to see what it looks like, what titration is. You can quickly YouTube, put in the YouTube search bar, titration demonstration or something like that. Okay. Now, the main focus of this lecture series for Chem 115 is determining, it's to build or create a titration curve. And so for us to further this topic, we need to address what a titration curve is. And so we're not going to be doing like simple titrations, simple titration calculations for Chem 115. What we're going to do is we're going to use our cumulative knowledge that we've discussed in this chapter to create a titration curve by hand. Dun dun dun. All right, and so what is a titration curve? A titration curve profiles the change in pH caused by successive additions of the titrant. And so here we're looking at how adding titrant changes the pH of the solution. And this is easily done in lab if you have a pH meter that constantly spews out these the resulting pH when a specific amount of titrant is added. However, when we do paper chemistry, we don't have this nice, beautiful, complex, expensive lab equipment to do all the work for us. We actually have to do the work by hand. And we're going to go ahead and take a look at that very soon. And so a titration curve just evaluates the change in pH caused by successive additions of the titrant. Now, we can use a titration curve for many different scenarios. And so one of the reasons why we want to build a titration curve or look at a titration curve is to identify the unknown substances. And so, for example, if you had a reference of all of the titration curves of known substances, and then somebody gives you in lab a mixture or a sample of an unknown substance, you can titrate it, look at its titration curve, and then compare it to the known titration curves. And if one of those curves matches, then you know the identity of your substance. Another reason why we want to build or look at titration curves is to be able to predict the pH if a certain amount of titrant is added. And I'll show you guys what a titration curve looks like in just a second. But when you guys are adding titrant, and if you guys have a profile of how the pH changes, you guys can use this graph to just kind of align these. You guys can use this graph to align where the points meet. And that tells you what the pH will be if a certain amount of titrant is added to the solution. We can also use the titration curves to identify if the substance, our analyte, is a strong acid, strong base, weak acid, or weak base. Okay. And the titration curves that we're going to be working with takes a look at all four of them. So we can also determine the pH at the equivalence point. So if you guys recall from first semester general chemistry, you guys were like adding drop by drop by drop by drop, right? Trying to make sure that you don't go over the end point or the equivalence point. And so what's really cool is that with the titration curve, you guys can automatically determine how much volume you need to add before you hit the equivalence point. And then once you guys are close to that equivalence point, if everything is measured out correctly, then you guys can slowly put, just drop by drop of the titrant into the analyte. But you wouldn't have to spend like the whole lab period doing drop by drops just to get to the equivalence point. And so there's lots more examples as to why we love or we heart titration curves. But these are just the common purpose of titration curves. All right, so let's go ahead and look at what a titration curve looks like. And so what you guys have here, one line is in blue, the other line is in green. I'm sorry, the one titration curve is blue and another titration curve is green. And so we're going to go ahead and take a look at one specifically for now, and then we'll go ahead and look at the other. But before we do that, we need to pay attention to the units as well as their location on this X and Y graph. And so notice that the pH is on our y-axis. Okay. Whereas the volume of the titrant added is in our x-axis. And so these two defines the what we're looking at in this graph. So we're looking at the change in pH based on the volume of titrant that's added to the analyte. Okay. So let's go ahead and take a look at the titration curve in blue. And so if you guys are following, maybe I'll do this in a darker blue. If you guys are looking at the left-hand corner, so here, let's just say that there's 0. So if 0 mils of titrant is added, the pH of that specific unknown solution is very low. So it looks like the pH is, let's just say it's 1. And so this is telling us that the pH of the titrant, I'm sorry, the pH of the analyte is 1. So it's very acidic. So we're starting off with a very acidic analyte. Now, as we continuously add titrant, notice that our pH is increasing. And so when our pH is increasing, that means that we're adding base to it, right? The only way to increase the pH is to increase the concentration of hydroxide by decreasing the concentration of hydrogen ion. And so the volume, as we add successive amounts of titrant into this analyte, the pH of the analyte is going to increase such that at one point it's going to have this like really steep jump. And then it kind of plateaus again. But if you guys look at this steep jump, notice that it went from like a low pH to a high pH. And so what that tells you is that somewhere along the line, you've completely consumed all of the acid that was in your analyte. And then at the very end, you just have excess titrant. And so since we have a high pH, that must mean that the titrant was a base. So we have excess base if we're looking at this titration curve. Now, what's really cool about this titration curve is that if we take the middle point, and there's many ways to quantify the middle point, and I really wish that we can do so. Maybe I'll develop a lab for it, a digital lab for it, if I have time. And so if we look at this middle point that I'm putting I'm coloring in orange, that's going to be the end point. Maybe I should not do this in orange. Okay. So somewhere along the middle of that steep increase is going to represent the endpoint. And the endpoint is where the equivalence point lies. And remember, the equivalence point is when the number of moles of acid is equal to the number of moles of base. So that's where the solution has been completely neutralized. And so if you have a titration curve that's representative in blue, that's represented by this blue curve. So if this is what your titration curve looks like, it tells you not only your it tells you not only the pH at the end point, but it also tells you that your analyte is acidic because we started at the bottom. It also tells you that if you added this amount of, it also tells you that if you added this amount of titrant, you get this pH, whatever this pH is. Okay. And so the volume of the titrant is typically expressed in milliliters. This also tells you that since there's one endpoint, that this is a monoprotic acid. In other words, it's just HA. Okay. Now, if you guys are looking at this green, it's getting kind of messy. I'm going to go ahead and let me just erase this. Okay. All right. So hopefully it's less messy. And so if you guys look at that green graph, let's go ahead and take a look at it in another curve, another light. Actually, I didn't draw it. Darn. Okay, never mind. So once again, if you guys are just looking at this green curve, you guys will see that as the pH increases by the addition of the titrant, at some point in time, we're going to reach this very steep curve going upwards, and somewhere in the middle is going to represent, once again, the endpoint. So this is going to represent the pH of the first endpoint. And so if you continue your titration, notice that you guys will have a second steep curve. And this second steep curve, once again, represents the pH. But instead of the first endpoint, it's going to be the second endpoint. And so if you guys are just solely looking at the titration curve in green, since there are two endpoints, then that must mean that our analyte is a diprotic acid. Okay. And so we're going to be profiling, we're going to learn how to calculate specific points on a titration curve that will allow us to build a graph that looks like this. Okay. And so the take-home message is that we can use the titration curve to figure out the endpoints. We can profile it to quantify or to determine the pH. If we add a specific amount of titrant, we can determine if it's a monoprotic acid or diprotic acid or triprotic acid, depending on the number of endpoints that we see. We can determine if the analyte is acidic or basic, depending on where the titration curve starts. So if it starts at the bottom has a pH of 1, so we know that's acidic. If the titration curve starts at the top and then kind of goes down or something like that, then since we have an initial pH that's greater than 7, then we know that the analyte is going to be basic. Okay, so there's a lot of things that we can conclude just by looking at titration curves. Okay. And so what we're going to do is we're going to learn how to calculate and build a titration curve. Now, if you guys are looking at this curve, there are infinite points on this black line. And so there's no way that you guys have time to calculate infinite points by hand just to develop one graph. And so what we're going to do is we're going to talk about very key points, very specific points in a titration curve that we can calculate within a decent amount of time. And then we're going to connect those points to build our titration curve. And so the first point that we're going to, that we need to calculate is where our curve starts. And so this point in blue, we need to learn how to calculate the pH. We need to determine the pH before the start of titration. Okay. And so during the titration, so somewhere here, so this is the first thing that we need to calculate. So actually, let me flip this backwards. Let me flip it upside down. Okay. So we're going to go ahead and calculate a couple points. And so we're going to look at, we're going to calculate the pH before the equivalence point. Okay. And typically we can just use one point, like for example, we can take this point or whatever, and we can use that to represent the pH before the equivalence point. We can also, so pH before equivalence point, so we can do this by calculating any point. So any point before the equivalence, I think that's what I just wrote down. Or we can use the halfway point. Okay. And so in other words, we're trying to represent this whole section of the titration curve by calculating one point before the equivalence point. Or we can represent that whole blue section by calculating the halfway point. And so the halfway point is, for example, here. And what defines the halfway point is half of the volume of titrant needed to reach the equivalence point. Okay. And so let me just be more precise, I suppose. So if this is the volume of the titrant needed to reach the equivalence point, then 1/2 of this value is the halfway point. Okay. So it's going to be 1/2 the volume required to reach equivalence point. Okay. And we'll look at several examples to calculate both of these. And last but not least, or actually not last but not least, so the third point. So we need to calculate the equivalence point. So that's the third point that we're going to have to calculate to build our graph. And then the fourth point. Okay. So this is the fourth point. It's just any point after equivalence point has been reached. So it's any point after the equivalence point has been reached. All right, and so overall, we have 4 separate calculations, 1, 2, 3, 4, or sometimes 5 calculations. And by determining at least one point that represent each of these key uh, places in the titration curve, we'll go ahead and draw our titration, we'll go ahead and be able to sketch our titration curve. All right, so that's pretty much it for this YouTube video, for this lecture video. Hopefully you guys got a better understanding of what titrations are, the theory behind titrations, and what titration curves are, and what we can do with them. And so in the next series of lecture videos, we're going to cover 4 combinations or 4 different types of titration curves. We're going to cover strong acid, strong base, strong acid, weak acid, strong base, weak base, strong acid. And we're going to profile all 4 of those scenarios. And the last video that you guys will watch, or hopefully will watch, compares and contrasts all 4 titration curves and what we can get out of it. All right, so I will see you guys in the next lecture video. Have a good one. Bye.